Welcome to another Hailo AI podcast, bringing you innovations and insights into AI on the edge. Now let's get started.
So thank you for having me. My name is Yaniv, and I lead Automotive at Hailo. In the next 25 minutes or so, I'm going to talk about the challenges of scaling AI on automotive. What are exactly is the challenge, and what are different ways to cope with it at the silicon level? Because at the end of the day, we all know that silicon today is powering AI in automotive, and as a semiconductor company, we're happy to offer some of our thoughts on this topic. So moving on, a little bit about us. We are a fabless chip maker based in Israel. We were founded more than 5 years ago. Our first generation is already in mass production. More than $200 million in funding from both financial and strategic investors. As mentioned, we're headquartered in Israel, but we have offices pretty much where the automotive industry is. Over 200 people today, and we have a growing worldwide partner ecosystem, including many partners in automotive. So having said that, looking a little bit about AI in automotive, and I chose maybe the most well-known domain which has grew AI in automotive to what it is today, which is both ADAS, the driver assistance systems, which I believe were responsible for the boom in AI in automotive to begin with, as well as automated driving. So looking at these two, which many times are combined hand in hand, I think, as shown in the previous presentation by Momenta, there are some unique challenges related to automated driving. So first, if we look today at ADAS has become definitely a market which is a large market, which is dominated by certain features that are required. It needs to comply with specific regulation. It is definitely cost-driven. And in comparison, when we talk about automated driving, we see it's mostly performance-driven today. We see an order or two of magnitude in performance more than ADAS in terms of requirements. Regulation is just starting in many places, and it's not well regulated yet. So cost has not become an issue yet. Of course, we all know it will be. And we look at some of the other properties, we see that the amount of sensors is higher in automated driving. We see that something which is pretty clear in automated driving, like comfort features for the passenger, are becoming more and more common in ADAS as well. And in general, we see that while these two are different, as an industry, we need to find the path to scale from ADAS to AD in spite of all these challenges. And one thing that both have in common is the fact that AI-based perception lies in the heart of both today. And we need a way to scale efficiently between the two in order to really have a roadmap path toward automated driving. And I think as an industry, we understand that we don't have a direct path to automated driving as maybe some thought years ago. The path is gradual. And if the path is gradual, we really need a scalable way to reach it. So moving on, let's take a look at a very popular term in AI, which is TOPS. So everyone are putting their requirements out in terms of what are these TOPS, which is trillion operations per second, and are required for processing, for AI processing in the car. So I'm taking a very rudimentary, basic example about a sensor that everyone would agree is needed in the car, which is cameras. If we look at the number of cameras that are needed, and then we multiply that by the frame rate of these cameras. Frame rate gives us the temporal performance, meaning how sensitive will these sensors be for real-time changes in the environment, in the vicinity of the car. So how fast will we notice those changes? Then if we look at resolution or pixels per frame, that will determine our spatial performance, meaning how sensitive we will be to small objects around the car. And then there is the element which is how well this model is designed for the purpose, or group of models is designed for the purpose that we want to achieve, which is accuracy. So in how many frames will we identify a pedestrian, as an example? And that's the model accuracy. So multiplying all these factors, we get to a number, which is our requirement. The challenge with that number is not only that resolutions change and frame rates change, is that in the AI world today, it's a very fast-paced world with a lot of advancement, and we see models that just yesterday we had models which achieved a certain accuracy and required performance X. Today they can achieve the same accuracy while consuming the half of the performance. As an example, in my next slide, I'm showing a wave of meta architectures called transformers, which are now making their ways into automotive. They're not in automotive today. Today in automotive, we still have more classical neural network object detection. But as an example, if we look at VIT, which is short for visual transformer, we can see that for the same level for the same level of compute, it can achieve higher accuracy, or it can achieve the same accuracy with less compute. And this tells us that in AI, it's not just about the tops or the requirement for a certain level of compute. It's the ability to leverage new AI architecture or meta architectures that we see that are becoming more and more efficient. And when utilizing them, we can actually lower the compute we need in the system. Continuing, going to the next slide, continuing the view on what we see in AI trends in automotive. So definitely when it comes to hardware, if we look at compute performance in automotive development cycles, which are roughly 30 to 36 months, we see that roughly performance needs have doubled. In every 2.5 to 3 years, performance needs have doubled. And that tells us that, of course, both power and cost efficiency are key, because if we keep doubling our cost and power, we have a huge challenge. And also we see that hardware is becoming more and more centralized. So while we had scattered ECUs in the car, each one having its own AI, now we see zone controllers and we see centralized domain controllers. And that means that we have a range of performance that we need to meet, and not singular point. When it comes to software, openness and flexibility are becoming more common, and if we want to allow for control and innovation in this world, then of AI in automotive, then obviously openness and flexibility are very important. We also noticed that software is a major challenge and has been a barrier to entry for many players into this market. And obviously the desired paradigm is to develop the software once and run it across multiple platforms. And in terms of the world of machine learning, the world of AI, we see advancement in the neural network models, and we see many tasks that were done with classical computer vision tools are increasingly being done with AI. And we see that AI is kind of on a class of its own in terms of compute and has grown and changed more in recent years than other classical forms of compute like DSP and CPU and GPU. And as I mentioned, I think one of the clear examples here is transformers, which is a new meta architecture for AI, which will be very dominant in many perception tasks going forward. Moving on, talking a little bit more about software. So we all know that software is today a core competency in the auto industry, and that we all know that software requires a lot of resources. But there are some specifics when we look at AI software in automotive. First of all, reuse. So reuse is crucial if we want to see return on the software investment that we make in AI in automotive. And as mentioned, since neural network models are changing, um, and the ecosystem is evolving, flexibility is very important. And last but certainly not least, many times when we talk about scalability, we think about it as a hardware requirement, but that's far from the truth. From the truth, the scalability is just as much a software requirement as it is a hardware requirement. The ability to scale in a linear or sublinear fashion when we scale up our number of sensors or taking on more AI tasks is equally as important in software. So looking at what we said so far, let's draw some conclusions about the challenge of AI in automotive. So we know that ADAS is cost-driven today, and it's a volume product. So we need an efficient way to scale to different levels. We've also discussed the fact that automated driving is a big leap from ADAS, and that scalability will eventually need to get there. We talked about the progress in AI and the fact that we will need hardware capable of running the latest and greatest neural network models. And we just talked about the software investment, which is really significant when it comes to AI in automotive. So the bottom line is we need a solution which is scalable, which is AI-centric, is centered around AI, and it is flexible and future-proof. So this is the conclusion from our discussion. And now in the next part of the presentation, I want to look at it from a silicon perspective and see what are the different options we have to get to a solution which answers this criteria. So when we look at the semiconductor world today and where technology is heading, we basically have three key ways to achieve AI hardware in automotive. The first one is monolithic design. So these are some of the many of the SoC players in automotive take AI IP, which is either homegrown or off-the-shelf IP, and they embed it into their designs for an SoC that will go into different applications in AI. Will go into ADAS, will go into automated driving, and to other applications requiring AI in the vehicle. So this approach, of course, is great because it's a single vendor from the hardware perspective. It's a complete solution, but it is also challenging in the scalability realm because when it comes to monolithic design, you will need to do you need a wide portfolio of devices to scale from the low end to the high end. It is very challenging, and the cost to achieve that is very high. And there's the danger from the OEM perspective of the lock-in scenario with that monolithic design vendor. Then technology in automotive is marching forward, and we can look at chiplet models becoming more relevant, meaning that a die a basic die of AI from vendor A can go into the SoC of vendor B and will be qualified and productized by them. This model offers much better scalability and flexibility than a monolithic design, but there are some challenges when it comes to qualifying and productizing these products for automotive. And then the third option is to separate the silicon to dedicated silicon for AI and dedicated silicon for other means. This is definitely the approach which has the highest scalability, but it requires multiple devices. So continuing this comparison on the next slide, here are some kind of, I would say, marquees to what are some example product targets that we see today in the market for monolithic design, for device level integrations, for platform level integrations, with some target performance numbers that some of you may argue with. I know it's a hot topic, but this is kind of an example, a representative example of where this can be. And of course, some of the device level integrations are still technologies that are in the making. So this might be more relevant for designs in the second half of this decade. And in the next slide, talking about how we view the proposed solution, we think that in light of what we discussed and the need for flexibility and scalability, we need a dimensional approach which separates the AI dimension from the other dimension of processing in the vehicle. For that, we need a creature that we would call automotive grade AI accelerator that accelerates AI independently from other compute needs. It offers scalability because you can grow or shrink it as much as needed. It is very power efficient and can fit passively cooled ECUs. It needs to be cost efficient, of course. And even though we have multiple devices, it needs to be cost competitive versus some of the mega SoCs out there. And it needs to offer an open software ecosystem and allow for software control and innovation by the OEMs and the tiers. At present, this solution is a chipset, meaning an ADAS SoC and an accelerator. In the near future, we view it as a chiplet approach, meaning a few dies that can be packaged as a single silicon. But the idea is there should be a single software investment behind the solution, whether it's a chipset or chiplet, that allows monetizing the software investment that is done in this architecture. So this is our view of the desired solution. And now I'll move on to the next slide and talk a little bit about, just summarize with what we do. So we are very focused on AI performance and doing it power efficient and doing it power efficiently. And moving to the next slide, just mentioning that today we have Hailo 8. This actually chip has been out in the market now for more than 2 years. It's a 26 TOPS AI accelerator. It is focused purely on AI and does not include other compute elements, and it is self-contained and can accelerate neural network, perform perception essentially models on its own. Moving on to the next slide, following the concept which I just mentioned, we already have reference designs with two major automotive players, both Renesas and NXP, in the same manner that I mentioned, which is combining an automotive SoC with powerful AI accelerator. Today is a chipset approach, which allows for application-ready hardware, which has a dedicated dimension for AI. And moving on, what we have today is, besides our device, we have different platforms with multiple, both single and multiple chips for evaluation and productization purposes. And I'll just summarize the next slide by saying that we believe that an AI acceleration approach and a path that includes separating the AI dimension from the other dimensions allow for one architecture and a seamless hardware concept. It is scalable. It allows for open software platform allowing reuse, which is a crucial point today since some of the other semiconductor players are offering software platforms which are not completely open, which might limit control and innovation, which we think is not the right way to go. And a long-term hardware concept from driver assistance to automated driving, as mentioned, which starts with chipset and we continue with chiplet. And specifically at Hailo, we're focused on building the AI dimension and making it power efficient and scalable and high performance. Thank you very much.
Many thanks, Yaniv. And we don't have questions in the chat. In that case, I jump in, if I may. Yaniv, if you would choose your pet unit of measure for useful work done on a chip, how would you describe the efficiency increase? You're nodding already. You think you know what I'm about.
Yeah, very good question. So if you've seen my presentation, you know that I would not measure it in TOPS. I would take a real benchmark, a real workload, and saying, okay, at running this neural network model for object detection, like a pedestrian detection, at this resolution, how many sensors can I fit on this AI chip, and what would be the power consumed? That would be a metric which I think is much better for benchmarking performance between different solutions.
If you can advertise yourself a bit, how does your product perform, if that is allowed to say?
Yes. So as an example, if I take one of the best, or today one of the most accurate object detectors out there from the YOLO family, like a YOLO V5 object detector, today our Hailo 8 device, you can fit about 7 automotive sensors at 30 frames per second, running this model on it at around 3.5 watts, as an example. So giving numbers, this is an example of real world performance.
Okay, thanks a lot. Meanwhile, may I encourage the audience to type some questions into the chat, and we do have some minutes, I think, because then I will ask again. You were talking about the neural network scalability, if I got that right, and then you connected it to the number of sensors. For example, if you scale in terms of sensors, can you explain what you mean? Just because there are people who say that one would try to stay away from sensors and the dependency of, for example, if the AI is a pilot, it should not care too much about the sensors. Did I get this right?
If the AI is what? Sorry? If the AI is?
The AI shouldn't be too dependent, or should not be unnecessarily dependent on sensors, the number of sensors, the type of sensors. If the AI is, for example, the autopilot, which ideally performs anywhere.
Yeah, so sensors do, I think, provide an important input because they they are the basis for any model that we run. So their input is important. I didn't try to say otherwise. It is very important. Um, the, the 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 scalability has many dimensions, and the number of sensors is one of them. But if we take as an example resolution, then our aspiration as system planners would be that the performance would scale linearly in resolution, and when we multiply the resolution, we will scale up in a linear fashion. In real world scenarios, it's not always the case, and sometimes when we multiply the resolution, the required performance is more than x2. And as an example, if that's what you meant in your question, I think a requirement should be, this is a scalability requirement, that when we scale up resolution, the performance of, of the device in question would rise in the same proportion as the resolution, as an example, regardless of the sensor, if it's a camera or a LiDAR or radar.
Thank you for listening to the Hailo AI podcast. If you enjoyed this episode, don't forget to sign up and check out more information at hailo.ai. Keep the conversation going by sharing this with your peers and never stop exploring the future of AI.